Hi, this is Mr. Mac, and this is the concept video on common logarithms and the change of base formula. Now, first of all, a common logarithm is a logarithm with a base 10. Now, common logarithms are such that in the United States, at least, everybody knows when you write log, and then if you put a number after it like 7, log of 7, and we don't show you a base, it is understood that the base is 10. And 10 is the base for what is called common logarithms. Now, if you look on your calculator, you will see on the left-hand side down, well, actually, where is it? Down to the right of the 7, a button that says log. That is a log base 10. So if you were to type log and then 10, for example, notice log base 10 of 10 would be 1, right? Well, the log of 10 is 1. So that shows you the calculator is evaluating that log with a base of 10. So what we're going to do is, it turns out that having a log of any base is good enough because of a thing in a minute that we're going to be talking about, which is the change of base formula. But actually, we could probably even get away without it, but it's a lot nicer to have it. So let's take a look at an equation that is not cooked. For example, 4 raised to the x equals 13. Now what we're asking here is, what exponent would you put on 4 to get 13? Now, we don't really know. I mean, 4 squared is 8, and 4 squared is 16. 4 to the 1 is 4, so 13 is somewhere between 4 and 16, so x has to be somewhere between 1 and 2, but we don't really know where it is. So, but what we can do to solve this equation is we can say, all right, we'll take the log of both sides. The log of 4 to the x is equal to the log of 13 by the one-to-one property of logarithms. Now, one of the properties that we talked about last time, and I said this is one of the things that makes logs so very useful, is when you're taking the log of a power, the exponent on the power can come out as a coefficient. So this can be rewritten as x times the log of 4 equals the log of 13. Now, if you notice here, this operation is multiplication. So to solve for x, we would simply divide both sides by the log of 4, which is some number. And so what we get is that x is equal to the log of 13 divided by the log of 4. Now, you can use your calculator because we do have a base 10 log, and that's what these are, common logs. And you can type log 13. And right here, guys, notice the calculator opens a parenthesis before the argument of the log. You've got to close that before you press the divide button, or you will get erratic, incorrect results, and nobody wants incorrect results. Then divide log 4, close that parenthesis again, and when you press enter, you get this number. It is 1.85021, etc. Okay, now, the thing is here, if you look back at the original equation, notice what x is. X is supposed to be the exponent of 4 that gives 13. Well, let's give that a try. 4 raised to the ands, and what do you suppose we're going to get? 13. Isn't that wonderful? Okay, so this is a way you can use common logarithms with the properties of logarithms to solve these questions. Now, what I'd like to share with you next is a formula that is called the change of base. And then we'll come back and we'll take a look at this equation a little bit more. So what I'd like to do is show you the formula for change of base. And here it is. Log base A of n is equal to log base B of n over log base B of A. Now, if you look at this with me for a minute, notice there is no b on the left-hand side of this equation. So if you want log base A of n, and let's say that's some base that you don't have a log button for, you can use a different base, a base b, because that's only on the right-hand side. And if you divide the log base b, whatever b you choose, of n by the log of a, you'll get the log base a of n. Now, we do need to prove this before we actually should be using it. So first of all, this is what we want to prove. Now remember, in a proof, there's a prover and a provee. In this case, I'll be the prover, you be the provee. And I am supposed to, we're supposed to agree on some place to start, and then I'm supposed to drag you kicking and screaming, grab you by the lapels, and drag you where I want to drag you, figuratively, not literally, with inexorable logic to the conclusion I want you to draw. This is the conclusion I want you to draw right here. So let's see if we can find some common ground to start with. I'm going to say, let's let log base a of n equal x. Now, I'm going to claim I can do that because x isn't in use at the moment. X can be anything I want, and so I'm going to let it be log base a of n. Now, since we don't really have the ability for you to communicate back with me, I'm just going to have to trust that you'll look at that and say, yeah, okay. If you have a problem with that, come in and see me. We can talk about it some more. Okay, so if this is the starting point, then what I'm going to do is I'm going to use the definition of logs to rewrite this logarithmic equation in exponential form, and it becomes a to the x equals n. Remember, the base of the log is the base of the exponent. The log is the exponent, so x is the exponent, and then n is the thing we get on the other side. Now, I'm going to take the log base b of both sides of this. I'm allowed to do that by the one-to-one property of logs. Log base b of a to the x equals log base b of n. But now I have a property of logs that says if I'm taking the log of a power, I can take the exponent of that power and put it out as a coefficient. So this is the same thing as x times the log base b of a. And that's equal to the log base b of n. Now, if I divide both sides, now look at this, x times log base b of a. If I wanted to solve an equation that said 2x equals something, I'd divide what x was being multiplied by. In this case, x is being multiplied by log base b of a. So that's what I divide both sides of this equation by, log base b of a. Now, look at this. This cancels with that, leaving x equals log base b of n over log base b of a. But now, let's go back and look at what x was originally. Originally, x was log base a of n. So where I see x way down there, I'm going to replace that with log base a of n. So I have log base a of n, that's what I'm replacing x with, is equal to log base b of n over log base b of a. Now, let's just go grab this and throw it down there and see if it compares with what we were trying to prove. Look, it's exactly the same. Ta-da! I told you so, or I'm finished, or however you want to interpret the QED. Now, what does this mean? And this is kind of important. What we're saying now is if you want the log, any base of any number, you just take the number, take the log of the number, your choice of base, usually we use 10 here, divide by the log of the base that you want, and you'll get that. Okay, now, there are a lot of examples where we're using this in the solution videos. You need to watch those. Now, let's go back and revisit this problem right here. Now, what we've got is we've got 4 to the x equals 13. Let's see, clone this and throw it. Whoa, it can go down farther than that, can it? Well, okay, there we go. Now, what we're going to do now is we're going to rewrite this equation in logarithmic form. See, we get x is log base 4 of 13, because remember, the base of the exponent is the base of the base, the exponent is the log, and the 13 is the argument of the log. Okay, but by the change of base, this is the log of 13 divided by the log of 4. And all we then need to do is take the log of 13 divided by the log of 4, which we already did. We got 1.8502198559, etc. So, once again, x is equal to 1.850219, etc. So you can use the change of base to prove, to solve logarithmic equations as well. And that is the concept that's wrapped up in Chapter 8, Section 6. Don't forget, watch those solution videos. Be sincere on your problems. These are important. We're done.